Let me first introduce myself, because you probably think, who's this guy and what did he do with Lauren? He normally gives these lectures. So Lauren has an invitation to London. I don't know if she told you. She gives a talk there. And my name is Martin Bauer. I did my PhD in Germany and am now a postdoctoral fellow at both the Enrico Fermi Institute here and at Fermilab, which is about an hour outside of Chicago. And in contrast to Lauren, I'm a theorist. So today we will talk about the Higgs theory. I will repeat some stuff. I guess some stuff I will talk about you already know. So if it's too slow or too fast, or if you have any questions, please interrupt this at any point.
That's it.
Okay.
We're all old. We can't see very well.
So this is actually him. This is Peter Higgs. This is the pictures he made once it was announced that he got the Nobel Prize. It's very funny when you look up on the web. The official pictures they did for the Nobel Prize, they all look very serious, but he decided to have a picture with the Nobel Prize. And most of this lecture will be about him and what he invented in the 60s last year. So this is a short outline, but I will, at some points I will deviate from this. I will just talk about something in more detail once it fits. But I will explain to you how the Higgs can be seen as a new, so far unknown interaction or a new force in nature. I will explain how the Higgs field gives particles their masses. And I will explain how the Higgs breaks symmetries. And there are a lot of buzzwords in there. You probably heard a lot of those before, and I hope I can clarify some of what is written in newspapers or on the internet and explain how it really is in theory. Let me first review what are the fundamental forces of nature that we know. And the one that we all know really well and that we experience every day is gravity. And the theory of gravity, the first really physical theory of gravity, goes back to the 17th century. At the core of it is that gravity is a force that acts on all masses. And it was Newton's accomplishment to see that the force that lets apples fall on the earth and that lets the moon go around the earth is actually the same thing because all masses attract each other. We also found out that once you go away from these masses, gravity becomes weaker. It becomes exponentially weaker with the distance that you set between you and the earth, for example. So this theory is still good today. It still can be used to calculate how the earth rotates around the sun, how everyday processes take place. But in the beginning of the last century, Einstein found out that is actually not all there is, because gravity does not only act on masses, but it acts on all forms of energy, which is not what we learn in school, because gravity acting on, like in our everyday life, every kind of energy we experience that gravity actually acts on is a mass. And the reason for that is that gravity is really, really weak. In order to see these effects that are based on Einstein's ideas, you have to go to really strong gravitational fields. But now we know it is true, and there are a plethora of experiments that actually prove that gravity does not only act on masses, but on all kinds of energy. And one very nice example is that light, once it is in a gravitational field, also reacts. And you might have heard from Noah's lectures so far that light is a massless field. Light particles do not have any mass. But we still see, in this experiment, for example, that light is bent by gravitational fields. What you see here in the middle of this ring is a big, red, very heavy galaxy. And exactly behind this galaxy, so actually in the line of view, is another blue galaxy. So if we are the observer and we would like to look at this other galaxy, there would be no way for us to see it if gravity would behave like Newton said. Newton said it only acts on masses. Light does not carry any mass. So actually, if this would send away photons, they would straight go like this. But they don't. They follow the gravitational field and they reach our eye. And what we see here is a galaxy that is exactly behind this one. The light of this galaxy is bent around this so that it can reach our eye, or in this case, the telescope that made this picture, which is a great example of how Einstein's theory must be correct, because it would never, nothing would happen here. We would never see this blue galaxy in this picture if it would not be bent by the gravitational field. It's called gravitational lensing, because the gravitational field here acts like a lens for whatever is behind it. The second force we know from everyday life is called electromagnetism. And electromagnetism acts on charges, not on energy, not on masses. And it's something we also see everywhere. Like, for example, this table here, the atoms in this table are all together by electromagnetism. We all are all together by electromagnetism. Because you might know that the nucleus of an atom is positively charged, the shell is negatively charged, and that we have dense macroscopic objects. The sole reason for this is that there is electromagnetism that keeps them together. And actually, electromagnetism is much stronger than gravity is. And in order to get a feeling for this, you could just look around you. Like when you take a step or when I jump, I beat the gravitational field of all the Earth, which is a pretty huge object. And I only do this by the electromagnetic interaction I send to my feet. The muscles in my legs are strong enough to beat the gravitational field. Or if I put something on this table, it's held together by electromagnetism. If it was really weak, it would just break through because the Earth attracts it. But the electromagnetism of this table is strong enough to keep all these objects up there and don't let them fall through, like air, for example. So to get a feeling, I would ask you a question. Look at this atom and assume it would not have, so you know atoms are really, really tiny, they are really small. If this would not be held together by electromagnetism but by gravity, the distance here would be much larger. The atom itself would be much larger because the force that holds it together would be much weaker. So take a guess, how big would your everyday atom be if it would be held together by gravity? As big as a baseball? More? Who thinks as big as a baseball? As big as this lecture hall?
Universe.
As big as the campus? Or the Earth?
As the solar system.
The solar system? Actually, it would be 1 million times larger than the So that goes to tell you how weak gravity really is. It's extremely weak. And it's actually one of the unresolved questions in particle physics, why gravity is so weak. We know a lot about gravity, and the reason is that gravity only attracts. That's a difference to electromagnetism. There are positive and negative charges. They tend to arrange themselves in a way that everything is electrically neutral. If I touch the table, this is fine because there are a lot of charges in this table, but they are set in a way that I don't hurt myself when I touch it. Electromagnetism is everywhere around us, but because it can repel and attract each other, it does not multiply the effect like the Earth does. Everything attracts each other gravitationally, so that is, even though it's really, really weak, we can experience it in everyday life. But there's more to it. If you look at this nucleus, you will see that it's not just one particle. It's made out of smaller particles, which we call neutrons and protons. And neutrons are electrically neutral, as the name says. Protons, however, are positively charged. I just told you, and all of you know, that positive charges repel each other, same charges repel each other, and only opposite charges attract each other. So there's no reason for this thing to stick together. Actually, if there was only electromagnetism and gravity, what we would expect is that it would burst, like the protons would fly around, they would repel each other, fly all around us, and there would not be like a compact system like the nucleus of an atom. Actually, there must be a force, they try to get apart, but there must be a force that is even stronger than electromagnetism that tells them, stick together, don't go apart. And this force is called, oh, actually here I put the number, it's a 1 with 36 zeros, the number, how much stronger electromagnetism is than gravity. So the force that keeps the nucleus together is called the strong nuclear force. And in many ways it's similar to electromagnetism. It's basically kind of a copy of it. There are charges, they are called color, because there are not two charges anymore, but multiple charges. And physicists like to make analogies, like positive and negative charge gives 0, but if you have multiple charges, if you sum them up, you don't end up with 0, so that's why they call them color. If you have 3 colors that overlap and they give white, you have a neutral object. So as in electromagnetism, stuff that is charged under the strong charge, the color charge, the so-called color charge, has to form something neutral in order to exist. It holds together the nucleus of atoms. It also holds together what the protons themselves are made of, because they are made of quarks. You might have heard this in Lauren's lecture as well. And these are color charged. That's why they build the proton to begin with. And this charge is about 100 times stronger than the electromagnetic. This force is 100 times stronger than the electromagnetic force. And you may make use of this. Here in Chicago in the 40s, Fermi built the first controlled nuclear chain reaction. Nowadays we have nuclear power plants. What they do in there is they break up the nucleus of a heavy atom and split it. And the energy that goes free in this process is coming from the strong charge that keeps the nucleus together. This is in contrast to your usual, like if you make fire or if you have a coal plant. If you try to win energy out of burning coal, for example, what you do is you take, it's chemistry. You take the electrons away from the coal atoms, they recombine, and the energy that gets free is the energy that bound the electrons to the nucleus. So this is the electromagnetic force that you break up and that you win energy of. Here it's the strong force. That is why these things are like 100 times more efficient. Well, you can be more efficient because this process has to be, you have to put in the initial energy to make it running. But these processes give you 100 times more energy per reaction as compared to a usual coal plant or if you burn gas or fuel. However, you could now ask the question, why are there no macroscopic objects held together by this strong force, like this table, for example? Why is it the protons and the nuclei? Why can't we build something would be pretty amazing, right? We could build like the hardest thing in the world if we just made it hold together by the strong force. And this is one of the most amazing things after the Einstein era that was found out. The strong force actually behaves completely different as the electromagnetic and the gravitational force. I told you, when you go away from the Earth, gravitation becomes weaker. If you go away from a charge, like if I take a magnet, for example, and you hold a magnet, and I go away from you, the attraction becomes less, right? But with a strong force, it's different. It's like a rubber band. Like, hold this rubber band, please. So now, if I go away from you, it becomes stronger and stronger, right? So this is the opposite as the electromagnetic or the gravitational charge. Color charges are bound more strongly once they get apart from each other. And this is a phenomenal insight that was not clear before. Because that also means there can never be a free color charge, which is not so easy to see. You have to know Einstein's formula for this. Let me show you this. So you all know this. Right? This means energy and mass are equivalent, or mass is a form of energy. When I take the rubber band and go away from you, what we do in order to hold it steady is we put energy into this, because there's a force that tries to put us together. Now, at some point, some of us would just let loose of the rubber band because it becomes too much for us to hold. But this is not what happens in nature. What happens in nature is the rubber band snaps apart in the middle. And in terms of this means the energy that we put in becomes mass. So if you take a positively charged guy and a negatively charged guy, these are your field lines that connect the two, right? The electromagnetic field. When I take them apart, they become thinner and thinner and thinner. And at some point, you basically don't see the other charge anymore. With a strong charge, that is different. With a strong charge, so let's say this is blue, and this is red. If I try to take them apart, the field lines become denser and denser and denser. It's completely different than the electromagnetic force. They become denser and denser. The force becomes stronger and stronger, and at some point, the energy that is stored in this force creates new particles, new mass out of the vacuum, like a red and an anti-red guy. And you end up with two new bound systems. But you can never get one of these guys by itself. It will never happen. The more energy you put into them, the more new guys you produce. Because it snaps and snaps and snaps. You have protons and protons and protons. You never have a quark by itself. And this was the idea of these three gentlemen, which got the Nobel Prize in 2004 for it. It's actually experimentally verified very well now. So these are 4 different experiments. This is energy. If I put more energy into it, that means I get closer and closer. I get the two charges closer and closer together. What we mean here is we shoot two protons to each other, right? If I do this with only a little bit of energy, they like bounce off, that's it. If I put more and more energy in, they get closer and closer. The color charges become closer and closer. And this is the coupling. It basically is the amount of strength of the strong force. So if I put only a little bit in here, it's sorry. This is the inverse. So if I put a lot in here, it's very strong. I should have taken another problem. It's very strong, and if I go closer and closer and closer, if I go closer and closer, it's very weak. So the upshot is the strong force is short-ranged in contrast to gravity and electromagnetism. I cannot feel the strong force of this table, although if I could feel the gravity if it was not just so extremely tiny. So there are more fundamental forces, and they are more mysterious than the strong force. There's the weak nuclear force. The weak nuclear force is really hard to picture because in contrast to the strong and electromagnetism and gravity, there are no bound systems that are held together by the weak force. It's strong, much stronger than gravity, but it's called weak because it is similar to electromagnetism. There are several charges, they cancel each other out, they don't multiply and add up like gravity, like the Earth, for example. But it's really important. Processes that we can observe, like the decay of the neutron into a proton and new particles, the electron, or in this case the positron and the neutrino, they are mediated by the weak force. It's another force that is very important for our understanding of nature. When I show you a process, you can see the difference between the weak and the strong force, because if you have the weak force, what happens most of the time is you add something that is not a composite object, right? A neutron goes to the proton and some extra stuff. With a strong force, it's always composite stuff with composite stuff. Yes?
Is it related to electromagnetism?
It is related. It is related to electromagnetism and to the Higgs mechanism. That is why I have to show it here, even though I can't illustrate it much better. So, I will explain this later. This force is also not something we can see because it's also short range. But the reason, as I just said, the reason for this is tightly connected with the Higgs mechanism. It has nothing to do with the reason the strong force is short range, which is the strange behavior that is stronger once I try to get away from it. Here, it gets weaker when I get away from it. But at some point, it just doesn't reach me anymore. This is hard to understand because electromagnetism, which is very similar to the weak force, does not work that way, right? I mean, even if I'm very far away from a charge and have a super detector, I can still see the charge. There's still an electromagnetic field. It's not the case here. And since last year, since the Higgs boson was discovered, there is in principle a fifth force in the game. Which some physicists will not allow me to say that because there are differences between these forces. They also only call the strong, the weak, and electromagnetism really a force, and would call this an interaction. But it is a force. There are particles where the Higgs boson or the Higgs fields acts on and mediates a force between those. And people somehow mix up the Higgs and gravity because there's always mass. You always have this thing of mass in your head. You read about it, like the Higgs give masses to everything. Gravity acts on masses. The real difference is, I just explained to you, gravity does not act on masses. Gravity acts on all kinds of energy. The Higgs couples to masses, only to the masses. So this is a better picture of a proton. A proton, there's a lot of stuff going on in the proton. There are 3 quarks, and they are held together by the strong force. And there's a lot of stuff happening. New quarks come up and they decay again, and there's a lot of connections here which are done by gluons, they mediate with the strong force. Actually, a proton, the weight of a proton, the gravitational field, is 99% the energy that is exchanged in the proton. The potential that comes up from all these strong interactions. If you would only take the 3 quarks that make up the proton, without strong interactions, like all of us would weigh less than 2 pounds, like 100 times less. But this is what the Higgs sees. So this is a proton, if gravity looks at it. This is the proton if the Higgs would look at it. It only sees the mass of these guys, not the mass that comes up from energy in these interactions. So now, we have seen all forces that we know so far in nature, and there are some differences and some common things that I want to emphasize. So we've seen gravity acts on energy, it's extremely weak, but the range is infinite, right? We we're still attracted to the center of the Milky Way, even though it's light years away. In physics, you would describe it by a spin-2 field. And that sets the character of the force. That is the reason why it's always attractive. Electromagnetic force comes on the electric charge. The strength is strong compared to gravity, it's much stronger. It's also infinitely ranged, right? But we never see this because it tends to build objects out of positive and negative charges so that they shield each other. It's described by a spin-1 field. Then there's a strong nuclear force. It acts on the color charge. It's very strong, even stronger than the electromagnetic force. But it's very short-ranged because when you try to get away from it, it gets stronger. When you're closer, it gets weaker. It's also described by a spin-1 field. The weak nuclear force comes on the weak charge, very similar to the electromagnetic force. There's a separate kind of charge. It's weak compared to these two, but still strong compared to gravity. It's extremely short-ranged, and I will explain why this is the case. It would be infinite if it was not for the Higgs. And it's also described by a spin-1 field. So all these guys can be attractive or repulsive. This, in physics speak, means they are described by a spin-1 field. Then there's the Higgs interaction. See, now I call it interaction. It acts on masses, not on energy, only on masses. Therefore, the strength really depends, because there are more massive things where the Higgs couples strongly to, and there are lighter things, or massless things, where it does not couple at all. It's also, like the weak nuclear force, extremely short-ranged, even though it's always attractive. So the Higgs actually would be similar to gravity if the range would be infinite. But it's not. It's extremely short-range, which is the reason we don't see it. And this is the reason for it. It's the only field that we know, fundamental field that we know, that has spin 0. So spin-1 fields can be both. Spin-2 and spin-0 fields can only be attractive. And that is also the reason, or one of the reasons, why people in physics tend to call this middle block, these three here, forces, and this interaction. Even though, like for layman definition, they will all be forces. They all communicate force. So fields seem to be important here. So let me explain to you what a field is. The short answer to this question is everything is a field. The best description of nature that we have is quantum field theory. And in a nutshell, that means everything around us, everywhere, are all kinds of fields. There's the Higgs field, the electromagnetic field, there are the quark fields. Everything we know can be described by a field. And if we see a particle, that's actually a wiggle in one of those fields. So let's say you are in empty space and there's nothing, then these fields are just 0. They are there, but they are 0. You will never see them. Now you get close to a charge. This charge, electric charge, makes ripples in the electromagnetic field. And this is what we see in our detector as a particle. Why quantum field? I mean, these are fields. At this point, there's nothing more to it. So what is a quantum field? The idea behind a quantum field is that even though everything is described by fields, we, at some point, don't see waves in a detector, we see particles. And this can be understood by an isomology. Imagine your friend has a lantern. And he takes this lantern and goes away from it. And he goes farther and farther away. And the light will become fainter and fainter and fainter. So at some point you don't see it anymore. But the reason for this is that our eyes are not perfect. If our eyes would be perfect detectors, we would see the light. It doesn't matter how far away he goes. But the point is, at some point, the light will not be a continuous wave hitting our eye, but it would be quantized. It would be bing, bing, bing. These are photons. These are the quantas of the fields, which we also call particles. So if I do a calculation, that we are working in this field, what we really do is we compute how a ripple of one field can leave its energy to another field. What we tell you what we do is, this particle goes into these two particles. And this is also what a detector would see. A detector sees, we send this particle in, these two particles we detect in the end. But what is happening, and the best theory we know so far, when we say particles interact, we mean one field acts on another field and excites a ripple in those. So this one loses some energy, becomes smaller, and therefore there are two new waves in a different field. That is how a particle can go into different particles. Now, the spin of a field, I introduced the spin even though I did explain some consequences of what it means that a field has spin, but I didn't really explain to you what spin is, and I won't do it. but I will go more into detail what we understand and what it means that a field has spin. Because there are actually everyday examples of fields that have spin. A spin zero field, everyday spin zero field, would be temperature. I told you there's only one known spin zero fundamental field in nature. That doesn't mean there are things that we can describe by spin zero fields or so-called scalar fields. Temperature is a good example. If you look at the weather map, you can observe that temperature assigns to every point in space and time one number, and that's it. So temperature is actually does not depend on the direction, right? So say we're in Chicago, it's 50 degrees or something. I look in this direction, I turn around, it's still 50 degrees. Nothing happened, right? It doesn't change when I turn around and move. Temperature does only assign a number. This is what we understand under a spin zero field. In contrast to a spin one field or a vector field. Wind is a good example of a vector field or a spin one field. A vector field does not only assign a number, but a number and a direction. So this is actually not a good weather map, because a good weather map would have the length of the arrows, would tell you how much wind you have in a certain place. This only gives you the direction. So the length would be what the temperature is, the number, but it will only tell you the magnitude of the wind. It will not tell you which direction it goes. Therefore, you need an arrow that shows you this direction. And vector fields are fundamentally different from scalar fields when it comes to space-time symmetries. Let me explain this. Say there's wind coming from here, and I look in this direction. When I turn around, the situation completely changed. Now the wind hits me in the face, right? It's not that nice anymore. And say I make a physics experiment. Say I take something like a piece of paper and throw it in the air. If I throw it in the air in this direction, it flies farther than if I would throw it in this direction. If I'm really bad off, I throw it in this direction, it lands somewhere there because there's a lot of wind. So actually the laws of physics in a wind field depends on in which direction I look. That is fine, but there must be a reason for this. We know that in space, when there's nothing present, no charge, no anything, all the fields are zero. Imagine there would be a field, like a wind field or an electromagnetic field in space that would have a constant value. Like for example, I look in this direction and there are reasons, there are pressure differences, there are reasons for wind. But if I would be in vacuum, there would be no reasons to have a non-zero field. This is what we call the vacuum expectation value of a field, what we would see when there's no source or sink present. We would expect that there's no wind. With temperature, it's different. Let's assume it's 10 degrees everywhere in the world. And on top of that, it's some more or some less. So that wouldn't actually change the laws of physics. I could throw my ball in any direction I wanted. It would not depend on the direction. This 10 degrees just rescale the temperature I measure at a certain point. It does not change how, the rotational symmetry when I turn around is not broken by a fixed value of a scalar field. It is broken by a fixed value of a spin one field. Now, if you remember, all forces are described by spin one fields, which basically means if we know that rotational symmetry is a good symmetry of nature, it cannot have a constant value. It's impossible. It would be like a wind field. It would just change how the laws of physics work, whether I look in this direction or in this direction. This should not be the case. So that means every fundamental field in nature, once I go out in space and I don't put a charge anywhere, the average of these fields just cancels out to zero. They're zero. There cannot be a constant background value or vacuum expectation value of a spin one field. The scalar field, just like temperature, is different. The scalar field can have a background value. And if everything sees this the same, if everything interacts with this background value the same, nobody would ever notice it. It's like a rescaling of temperature. But let's say you, for example, are very sensitive to temperature and you feel this 10 degrees difference actually. You would say, come on, it's very hot today, and I do not. So for you it always feels much hotter than for me. Then there would be a difference because you would experience the world different than I do. Right? If nobody recognized this 10-degree difference everywhere, it would not matter for the laws of physics. But if people, in the case of temperature, or fundamental particles, in the case of the Higgs, see the field differently, then it actually makes a difference. And let me emphasize, there's no good reason why there should be a background value. I said the scalar field can have one, and it doesn't break rotational symmetries and stuff that we know is true, but it does not have to have a constant background value that is not zero. It's just the only field in nature that can have one. And the interesting thing is, it does have one. It's very strange in a way, because it's very easy to write down a quantum field theory where every field has a background value, a background expectation value that is zero. But if we observe nature, this is not actually the case. The Higgs, the only field that in principle can have a constant background value, has a constant background value. And what I just told you really happens. Different fields see, or different particles see this background value different. Like for some fields, for some particles, the Higgs background value is like swimming in honey. They just can't get forward. This background value slows them down. For other fields, the Higgs background is completely transparent. They just go through, like photon. Light, for example. The light goes from this projector to this screen because it doesn't care about this constant background value. It just goes through. Now, I told you the weak force is short-ranged. And the reason for this is it sees this Higgs background value very well. It doesn't come far. So if you go back to this lantern example, for example, can you use a good analogy again? Imagine there's really thick fog and someone holds a lantern. If you're really close to that person, you would see that there's light emitted from the lantern. You would actually recognize that there's an electromagnetic field. But as soon as it goes away from you, it vanishes. The fog shields this field from you. And this is exactly what happens with a weak force. It's a really great find. It's a great theory that it can explain the masses, because it slows down some particles and some not. And it can explain why the weak force is weak, or short-ranged. It's short-range. It's called weak because at long distances you basically don't see it. When you get close, it's not that weak at all. But it's short-range because the background value shields you from the force carriers that mediate the weak force. And this is also a choice that nature would not have to make. So you mentioned that the weak force and the electromagnetic force are basically the same thing. Actually, if the Higgs would have a zero background value, they would be exactly the same thing. It's called electroweak force. Once you set this background value to zero, there would not just be one light particle, there would be 4 different light particles. All would be massless particles, because there's no Higgs that can shield them. All would transmit long-range interactions, and we would see them. Everything would shine in different lights in a way. So, for some reason, nature has decided the one field that can have a background value has one. Some particles see it, they are heavy when they try to move through it. Some particles do not, they are massless and move with the speed of light. Some particles that transmit interactions don't care about it, like the electromagnetic field just doesn't care about the Higgs. Some particles that transmit immediate interactions, like the weak force carriers, they are the particles that mediate the weak force, they see the Higgs very well and they don't get far as long as this Higgs background value is on. It's also the reason why the Higgs force itself is short-range. I told you, it's always attractive. In a sense, it could work like gravity, right? If it would be long-ranged, it would multiply its force. Once there are multiple Higgses, they would just mediate stronger and stronger attraction, because there's nothing to repel it. But the Higgs background value shields its own force. The weak and the Higgs interactions are both weak because they are slowed down by a constant background fog, which we call the vacuum expectation value. So now you can ask the question, why is it that way? I told you, a scalar field can have such a background value, but it must not have such a background value. So in physics, you describe such a scenario by the potential of such a field. You could easily imagine a potential where the Higgs sits at 0. This is where these x's crosses 0. And a potential like this, like a solid bowl, would have the Higgs always roll to the point where it needs the less energy than anywhere else, and that would be 0 in that case, which would translate into 0 background value. But for some reason, the potential of the Higgs looks like this. At 0, it actually costs the Higgs energy to sit. It's not balanced. The Higgs wants to roll down to a finite value, which is this background vacuum expectation value I described. And theoretically, there's no reason for this. It just works. Higgs wrote down this theory and said, look, once we have this, the weak force is short-ranged. Once we have this, we know why particles have masses. The question why is not answered, and it's not answered till today. It's actually one of the reasons that LHC will go on in a few years from now, 2015 I think, and we'll search further because we want to know why. We want to know why it looks like this and not like that. They're brilliant ideas, but so far nothing besides the Higgs itself has been seen. And actually, this whole situation is described by the very same physics. As a theorist, I can tell you this, the exact same physics that describe phase transitions in matter. So, the water, for example, can live in different phases. You all know that. It can be vaporized, it can be liquid, it can be ice. And this is a phase diagram of water. Because the behavior of water depends on the temperature and on the pressure. If you have no pressure and very cold temperatures, you have ice. If you put a lot of pressure, it will melt. If you raise the temperature, it also melts and can vaporize at some point. This is a phase diagram. Water can be in completely different phases. The same is actually true for the Higgs. Only now the parameters that tell us whether the Higgs sits in this little bump I showed you or moves somewhere else are different parameters. It's the mass of the top core and the mass of the Higgs itself. The mass of the top core, we know, it was actually measured at Fermi, like an hour from here in the 90s. It's the last fermion of the standard model that was found. The top core is very heavy, it's even heavier than the Higgs. You can see that. It's somewhere between here. While the Higgs mass, as you all know, was measured last year. So now we know these two parameters. We know the phase the universe sits in. And this is very interesting, because many theorists would have expected that we sit somewhere here in this green area. So you could say this is somewhat confusing. Here I give those things names, and the reason is that actually I can sit down and change temperature and pressure, and I can let water go into ice, and I can water go into vapor. I can change the phases. The phase of the universe, at some point during the early universe, the Higgs has decided where it sits. I cannot change the mass of the top core, I cannot change the mass of the Higgs. These are fixed parameters. But there's a phase-space diagram anyways. And people thought we would be in a stable vacuum. That would mean, let me show this actually. That would mean the Higgs potential actually looks like this. And this is where the Higgs sits. So it can never ever leave this thing because these walls go infinitely high. But the Higgs potential, as I said, this is just one way to write this theory down. We don't know what the Higgs potential really looks like. It could look like this. And the Higgs sits here. So there is a deeper potential sink somewhere in this mathematical formalism where the Higgs really wants to be. And actually, because of quantum mechanics, at some point it can be there. It will not have the energy to go over this hill in a sense, but it can tunnel. There are tunneling effects in quantum mechanics, so the Higgs has a way to go there, which would be really, really bad. Because at that point, all the things I described that would happen in a world without Higgs would actually come true. Like there would be no background value, the light would be made out of 4 particles, everything would be massless, things would fly from each other and all that stuff. So this should not happen. This is why people thought we should be in this stable area. But now the Higgs mass is measured. Actually, the red area is complete instability. That would be exactly this. Then there's some area between those two, which is called metastability. That just means that these parameters are not measured perfect. There are some uncertainties in there. There are always uncertainties once you measure something in an experiment. And this is the area that is given by this uncertainty. It basically tells you this could happen, but maybe not. This says it will, this says it will never. And now, since the measurements are in, we know we sit exactly in this yellow area, which means our universe, if the standard model, everything we know so far is everything there is, the universe is not really stable. Maybe tomorrow the Higgs tunnels to its new vacuum and everything flies apart. But it doesn't look that way, right? The probability would be very low anyways in this area, but it doesn't look like that would happen at all. And this you can interpret as a sign that we don't know everything. whatever tells the Higgs to sit there and not somewhere else, the Higgs mechanism that makes the Higgs take on this specific value must somewhat stabilize this. And if you add in new stuff, like you write a theory where there are new particles, new interactions, then this phase-space diagram changes. So you might read in the newspaper, or there are even famous physicists that said, now since we have measured it, we know the universe is beta stable. That is completely false. We know nothing. We know it looks like there's more. That's the way I would interpret this plot. It looks like the universe is not beta stable because we don't experience happening anything. The Higgs doesn't tunnel anywhere. But we know it would be according to this plot and according to all the matter and all the fields we have discovered so far. I add one new field and this completely changes and we might be in the stable area. This could be a first sign that there is new stuff, and in my opinion it really is a sign of new physics we have not discovered so far. But I want you to take away from this that the physics that tell water to be liquid or to be vapor are exactly the same that describe whether the Higgs sits in a stable or metastable vacuum, and you can draw such a phase diagram actually for the universe, for the substance that everything is made of. There's another similarity to this. If you ever looked at water in open space, which you probably did not, or you were lucky and could manufacture it yourself, if there's no gravity present, water looks like this, like liquid water. It's completely spherically symmetric. If you can turn this drop around in any direction, it still looks the same. Once you change the phase and you go from one phase to another, to the solid state, water has a different symmetry, right? I mean, some people would say this looks nicer than this, but this has less symmetry than this guy. This I can also rotate, but only at certain angles it will look the same. So in one phase, there is a higher degree of symmetry than in a different phase. And that is when you read or hear about that the Higgs breaks the electroweak symmetry. If the Higgs value would be 0, the degree of symmetry in the universe would be higher. Say I have 4 particles, they are all massless, I can exchange them, nothing changes. There's a higher degree of symmetry than I have 1 particle, which is light, and the other 3 are some strange weak force that only interacts on short distances. So if the Higgs would actually sit up there at 0, you can also see it in this plot very easily. You can turn this plot around, it looks the same, right? Once the Higgs decides where it sits, here at the finite value, this symmetry is broken. It's not there anymore. I cannot turn this around. Once I turn this around, actually it changes, right? So in that way, the Higgs mechanism gives masses to particles, it shields the weak force, and also breaks the symmetry, namely the electroweak symmetry, which we now know in the unbroken phase is completely restored. So before I finish, instead of a summary, let me explain to you what are the open questions that we now search answers for that have not been answered by the discovery of the Higgs. Because I think this is really, really important, and a lot of politicians don't think that. Like there are politicians in your country, I read statements that basically said, so now we have it, everyone, we can get everyone home now, we have discovered the Higgs, we know everything, that's it. That's not the case. This theory is nice and explains a lot that was not explained before the Higgs was discovered. Actually, if they would not have seen the Higgs, we would stand here and we would actually, there would be a lot of question marks in my head and around these theories, because we would not know where the mass comes from, what the weak force really is, the character of this. All these questions are now answered. But there are also questions that are not answered at all. The most pressing one is, what tells the Higgs to be in this state? And the standard model, together with Higgs theory, which is now part of the standard model, does not explain this question at all. There's no reason at all. Once you write it down, you decide where the Higgs vacuum is. And you have to write it down in a way that tells the Higgs to be at this specific point. If you don't do it, you end up with a completely wrong theory. So now you can say, why is that such a big deal? I mean, there's a lot of stuff that is not explained, which in the end turns out to be just numbers, like the mass of whatever we measure. We don't know why the mass is what it is. We just measure it and put this number in, and then we end up with the right theory. But here, and this I can unfortunately not really explain in detail, it's even worse. So for all the masses we measure in nature, actually once we measure them, the quantum character of these theories tells us, that's it. It should stay where it is. With the Higgs, that is not the case. You have to tell the Higgs where it should be, and then you start doing calculations, and you see that the quantum character of these theories actually want this to go up. They actually want the spectrum value to be much, much higher than we really measure. So there are two sides to this question. One is why it is the value that it is, and the second is why is it stable, why doesn't it change under quantum effects at all. Another big question that is only slightly related to what I showed you is, where's the graviton, for example? I told you everything is described by quantum fields. We have a completely consistent theory of every field. Gravity is not part of this theory. The reason is that gravity is so extremely weak that if you want to make a ripple in a gravity field, you need an extremely strong gravitational source. So people look at black holes and they look at supernovae, exploding stars where really a lot is happening, that maybe they are the way, these make waves in the gravitational fields where you can finally find the graviton. Because even though this theory looks nice, it doesn't have to be true, right? If we never see the graviton, this is not what nature is. And then the Higgs allows us to understand how the electromagnetic force and the weak force are actually the same thing. But there are more forces. Strong force, gravity, all these forces seem to be different. They behave different. They seem to have a completely different character, even though there are some things that are common between them. And why they are so different, there must also be something that tells them to be different. Why is it not the same? Why don't they behave similar? We try to understand the physics behind this. That's basically it. Oh, right. To make perfectly clear, there's a lot of confusion between these three words. I want to make perfectly clear what they mean. The Higgs mechanism is this process. Telling the Higgs, go to this vacuum. This is the mechanism. The Higgs field is the field with which we mathematically describe every other particle has its own field. The Higgs has two. The Higgs spectrum expectation value is the constant value of this field in empty space. And the Higgs boson would be a ripple in this field. The Higgs boson does not give mass to anything. The mass is this constant value. The Higgs boson actually is a new kind of force that happens between two particles, and that is proportional to their mass. But the boson is just a ripple in the field that is responsible for the masses, and is what we really see when we see something happening in the detector. That's it for today, and thank you very much for your attention.